Good morning, everyone. My name is Pranay. I'm from CSC AML Section C. Today, my subject ordinary differential equations and vector calculus. In ordinary differential equations and vector calculus, my topic is particular solutions of homogeneous equations. So, introduction. I would like to start with introduction that homogeneous differential equations are the derivative of a function which depends upon the ratio of dependent and independent variables. These equations are widely used in mathematics, modeling, physics, and engineering due to their symmetry and scalability properties. A first order differential equation is said to be homogeneous if it can be expressed in the form of dy by dx is equal to f of y by x. If any differential equation is in the form of dy by dx and dy by dx is equal to f of y by x, then it is said to be first order homogeneous differential equations. This means that the function of the right hand side depends upon the ratio of y by x. Such equations exhibit a key property. That key property is called as scale invariance. That meaning is if both variables are multiplied by the same constant, the equation remains unchanged. So to solve a homogeneous differential equations, let us follow this method, and I'll be explaining this method. We use the substitution. First, let us take v is equal to y by x. This can also be written as v is equal to yx. Now, on differentiating on both sides, what we get with respect to x is dy by dx is equal to v plus x into dv by dx. Now, let us start rearranging. Now, x into dv by dx is equal to f of v, function of v minus v. So, on rearranging, we have got x into dv by dx is equal to f of v minus v. Now, this equation can be solved using separation of variables leading to the general solution which contains arbitrary constant. The general solution, it is nothing but it represents a family of a curve, while particular solution, it is obtained by applying initial or boundary condition. This condition helps to determine the value of the arbitrary constant, thereby selecting one specific solution from the family. Now, let us solve a problem. Now let us solve a problem and let us do the procedure. And I have brought two examples to solve, and this is first example I am explaining. For example, consider this differential equation dy by dx is equal to x plus y by x. Now how can be this written as? This can be written as dy by dx is equal to 1 by y plus x. Now what you do is substitute it in the equation v into x plus dv by dx is equal to 1 plus v. By substituting in the equation, we get that v into x into dv by dx is equal to 1 plus v. Now, by simplifying, what we get is dv by dx into x is equal to 1. That is, x into dv by dx is equal to 1. Now, on integrating on both sides, we get that v is equal to log x plus c. Now, substituting in the equation, y by x is equal to log x plus c. That is equal to y is equal to x into log x plus c. Now, this is a general equation. Now, to find boundary condition, we have to take a boundary or initial condition, right? To find a particular solution. So we use the condition y of 1 is equal to 2. Now let us start keeping substituting y is equal to 2. What is the equation we got? Y is equal to x plus x into log x plus c. Now 2 is equal to 1 into log 1 plus c, that is equal to c is equal to 2. We get it. Therefore, the particular solution is y is equal to x into ln x plus 2. Right. Geometrically, what happens is the general solution, it represents the family of curve, but the particular solution represents that specific curve which is passing through a given point. So, in the above example, we have seen that the y is equal to x into ln of x plus c, it is the general solution. But when we are taking a boundary or an initial condition, when we are initiating the boundary or an initial condition, we came to find out that the particular solution is in that particular solution, the value of c is equal to 2. After getting the value of c equal to 2, what is the particular solution we got? The particular solution we got is equal to y is equal to x into ln x plus 2. So geometrically we see that general solution, it represents a family of curves, and the particular solution represents that one specific curve passes through a point. Let us assume that the point is 2. Right. Now let us continue explaining our applications. In worldwide applications, these homogeneous differential equations are very important, because in worldwide applications there are many applications where we apply these homogeneous differential equations. First is fluid flow. In case of Bernoulli's principle, I think many of you here know Bernoulli's principle. Bernoulli principle focuses mainly on the concept of explaining the fluid flow. So what is Bernoulli's principle? Bernoulli's principle is nothing but as the speed of moving fluid increases, its pressure decreases. So according to ODVC principle, that is ordinary differential equation principle, let us assume P plus half rho v square plus rho g h is equal to constant. Now what we do is P1 plus half rho v1 square plus rho g h1, P2 plus half rho v2 square plus rho g h2 rho 1, let us take it as constant. This is the one of the principle that we apply in our ODVC, that is ordinary differential equations and vector calculus. Now electric circuits. How we apply electric circuits in differential equations? So Laplace transformation, one of the application. So what is meant by electric current in ODVC? In our electric current in ODVC, that is, so what is the application is Laplace transformation in ODVC. See, electrically current is modeled to analyze how flow of charge and flow of electrons, all those takes place. So when L is conductor, R is resistor and C is capacitor are involved, what we'll use is we'll use a first order, second order differential equation. I is equal to dq by dt, L is equal to di by dt. So L into di by dt is equal to Ri, that is equal to E of t. RC circuit, R into di by dt is equal plus I by C equal to dE by dt. L into d square I by dt square is equal to R into di by dt 1 by Ci into dE in dt. So these are some applications that we use in our electrical circuits. Let us also discuss about key mathematical concepts applied. First is solution of ODE, next is transistor response, next is steady state response, next is Laplace transformation. Physical systems where proportional relations exist in vector calculus, these are related to directional fields and integral curves, so helping the describe the behavior of vector fields. In conclusion, I would say that in concluding in a short, the finding particular solutions of homogeneous equation allow us to move from a general mathematical model to a specific real world solution by incorporating given conditions. Now let us solve another example. We see that dy by dx is equal to 2x plus 3y by x plus y. Now substitute v is equal to y by x, v is equal to y by x, y is equal to vx, dxy by dy equal to v into x into dv plus dv. Substitute equation v into x plus dv is equal to 2x into 3 of vx and by x plus vx into 2 of 2x plus 3vx by x into 1 plus v, that is 2v plus 3v by 1 plus v. Now we got x into dv by dx is equal to 2 plus 3v by 1 plus v minus v. On simplifying, we get 2 plus 2v minus v square by 1 plus v. X into dv is equal to minus v square of minus of v square minus 2v minus 2 by 1 plus v. Now on variable separable method, we get by y equal to x into v. This is the general solution. By keeping into particular, taking y1 is equal to 2, we get x equal to 1, y equal to 1, y is equal to x. That is the solution. In this session, we have explored particular solutions of homogeneous differential equation, we saw how they plays a crucial role in moving from a general mathematical model to a specific solution that satisfies given condition. So here are some key points to remember. Homogeneous equations depends upon the ratio of y by x and the scale invariant. Substitution v is equal to y by x simplifies them into separable equations. The general solution represents family of curves, while the particular integral is determined by initial or boundary condition. These equations have broad classification in physics, engineering, and vector calculus, including modeling, motion, fluid flow, electrical circuits, and vector fields. Understanding particular solution allow us to predict system behavior accurately and apply mathematical models to real world problems. With this, I would like to conclude my topic, and I thank each and everyone for giving me this opportunity. Thank you. Thank you once again.